and in this talk I'm going to talk about the cosmology with the bright standard sirens. So, first of all, what will be or what is bright standard sirens? Standard sirens is a source of gravitational waves in which we can measure his luminosity distance. It's an analogy with the standard candles, so they receive this name standard and sirens. But there is a difference between the standard sirens. There is those ones that have don't have an electromagnetic counterpart, that is called dark standard sirens, and these ones that have an electromagnetic counterpart, that is the bright standard sirens. And this comes from, for example, the coalescence of binary neutron stars. Imagine an electromagnetic counterpart. It can be an isotope, like a kilonova, or a beam electromagnetic counterpart, like a short gamma burst. So, from the theory of the general relativity theory, we know that the amplitude of the gravitational waves is inversely proportional to the luminosity distance, and this is the reason why they call it the standard sirens. And if they have an electromagnetic counterpart, they are bright standard sirens. And we have only one level of this. There is the GW17 or 1817. Then whose one will use this element to measure the Hubble constant with an uncertainty of around 12%. And this is the only one element of this type that we have. And we want to have much more of these elements in order to make all the cosmology. So, what we have with our detectors? We have the current gravitational wave detectors that are the LIGO, two LIGO in US, in Hanford and in Livingston. Other ones, the name is Vigo in Italy, and other one, Kada in Japan. And with these detectors, we can use the signal coming in these detectors in order to estimate all the parameters of the event. And one is the luminosity distance. So this is the matching filter. We have the output of our detectors. Where is the output of the detectors is much have a noise here, and we can extract the gravitational wave source in this output. And we do this using the matching filtering. That is comparing the output with detectors with a lot of templates in order to match the output with original gravitational wave signal in the output, okay? So, we have, with the current gravitational wave detector, we have the sensitive curves in respect with the frequency, and if we have the signals in Fourier domain that is above this curve, we have detected this gravitational wave signal. And it's a threshold that we have. If we have signal with a signal to noise ratio above H, we can have let me see. We can see a real gravitational waves in the output. Okay. So in this plot, I'll show the relationship between the redshift range of the source with respect to the total mass of the source. If one detector is inside the shaded curve, we can detect the source. So we have our range in binary neutron system with the current detectors in this range of masses. We can achieve with the current detector up to redshift 0.1. With stellar black holes, we can achieve a range of at maximum 1. And with the other mediated binary black holes here, we can achieve the redshift around 0.8, for example. Okay? But we are interested in detection of bright standard sirens. In order to make cosmology, we want to go much more distance events to make the cosmology much more precise. Okay? So we will have in the next decades the third generation gravitational wave detectors. We will have the Cosmic Explorer in US, the ICE telescope in Europe, and first spatial detector, that is the LISA. And with these detectors, we can achieve distance much more higher than the current ones with the LIGO video integra. For example, with binary neutron system, ICE telescope and Cosmic Explorer can go up to redshift around 6 or 7, and this is good for us to perform cosmology. If we can, a lot of binary neutralized system with electromagnetic protocol up to this redshift, we can make good measurements of cosmological parameters. One of them is the Hubble constant. Okay, so in this presentation, I'm going to show some forecasts on cosmology with bright standard science using the arXiv telescope or Cosmic Explorer. So to do this, we have to simulate distribution we have to simulate detection of binary neutralized system with electromagnetic protocol. With a given distribution of this source, this here is one estimated distribution for bright standard science with electromagnetic protocol with a peak around 0.5 in redshift. So, but we have also to have estimations about what will be the precision in the measurements of the luminosity distance with this the third generation gravitational detectors. So we have this curve here is the curve related the estimated uncertainty in the luminosity distance of binary neutral star with respect to the redshift. And this one is the error related to the lensing, gravitational lensing. So this blue one is the combination of all the uncertainty that will be had with the measurements of luminosity distance. Okay. So we expect that with the arXiv telescope combined with other electromagnetic detectors like these used, that we will have a total number of 100 detections in 10 years of observation in the pessimistic scenarios, and in the optimistic scenarios we can achieve around 500 detections up to a redshift 1.6 in 10 years of observations. This is an estimation. And we use this one to perform now our simulation of the relationship between luminosity distance versus redshift. And with this set of data, we perform all forecasts on cosmology with bright standard setting because we have the measurement of the redshift. Okay. So, but one point that I want to mention is how can we get the redshift of the source? The point is that if we have a source with electromagnetic protocol, we can use this electromagnetic protocol to identify the host galaxy and consequently use the redshift of that galaxy and perform a relation with the luminosity distance. Okay? We don't have this with dark science. Okay, one of the forecasts that we can do is the Bayesian model selection. That we can compare a lot of cosmological models and confront them with the data in order to estimate if a model will be more favored with the data or no. So in this work, I simulated my data set of luminosity distance with redshift following a lambda CDM model. So, and with this set of data, we face this data with all the cosmological models, the nested cosmological models, and compare what will be the more favored cosmological model with this data, and how much detection we can have in order to infer that the lambda CDM model will be much more favored with the data than the other ones. And here we show the results that we can achieve a weak evidence favoring the lambda CDM when we get around 100 number of detection compared to model lambda CDM with omega CDM or lambda CDM with omega 0, omega 8 lambda CDM. But if we reduce the errors in luminosity distance, for example, with other detectors like the Cosmic Explorer and other detectors, if we can reduce the error up to the level of gravitational waves, for example. So if we reduce the uncertainty, we can achieve much better results in this evidence. We can achieve a moderate evidence when we get around 400 detections. And here's one example of how can improve the uncertainty, the luminosity distance with other detection. For example, if we have only the arXiv telescope, we will have this over here, related the uncertainty luminosity distance with the redshift. We have this one here in blue. If we have only the Cosmic Explorer, we have this one. This is using a Fisher-Metric approach. And if we combine the arXiv telescope and Cosmic Explorer, we have this red group here. And we have, for example, a nice telescope, a Cosmic Explorer, and the other, for example, other detectors. You have this black hole here. And in here we show how can we improve the measurements of luminosity when we have much more detectors joined with the arXiv telescope. And here is one example. If we have an arXiv telescope here in Europe and a Cosmic Explorer here in US, what will be the best place of a third generation, a third detector in surface of Earth in order to have better results in the measurements of luminosity distance? So this plot here shows the dark regions here show the best place of a third detector, and the lighter ones here is the worst regions to put a third detector. So this is again, this is only a forecast using fusion metrics. Okay. And here I show another cosmological analysis with bright standard science. There is this cosmography with bright standard science using arXiv telescope. Here I will be compare the data of luminosity versus redshift of a binary neutron star with electromagnetic report, and we will face these results with cosmographic modeling of this relationship. So we can use the same simulations here, this one, and instead of making model selection, we can make a parameter estimation of cosmographic parameters and show what will be the precision in the measurements of these parameters, the H0, the Hubble constant, the Q0 related to the acceleration parameters, the J0 related to the third derivative of the scale factor today, this green one, and this show the relative uncertainty of the lumen of these cosmographic parameters in function of the redshift. That is, we are accumulating detection with the redshift up to get a total number of one of this one here. When the curve is darker, when we achieve a total number of 2000 detection up to a redshift 0.7, and 125 when achieve 0.7 redshift, this light curve here. And this dashed curve here is the case when we can improve the measurements of the luminosity distance up to 20%. That is the comparable with that ones of the gravitational lenses. Okay. So this is a parameter estimation of this cosmographic parameters using the Pantheon data, the supernova, and we show here how many detection we can get with the bright standard science in order to get better results with those ones using supernova. And here is the relative uncertainty of the cosmographic parameters, blue ones for H0, red for T0, and green one for J0. And here in x-axis we have the total number of detections, and we show that the solid one is that one related to the estimated uncertainty luminosity distance, and the dashed one is that one when we can reduce the uncertainty luminosity distance. And we show that if we have a total number of 750 detection, we can get uncertainty comparable with that one of supernova. But if we can reduce the luminosity distance, we have ever have better results in the measurements of the Hubble constant, P0 and J0. Okay, and that's it. And thank you very much.